Okay, today's talk is about linked lists. Before we talked a little bit about memory management and we talked about the heap and the stack. We continue this now. Discussion of linked lists. What I want to assume here is I have declared this thing over here. I've called it an A node, public class A node, and there is nothing really too unusual about it. Whoops, that's not working. Now it's going to work. So I come over here, and if we just were to draw a picture of what this thing looks like, it's got three fields in here like this, and over here there is an int age, and over here there is a double, and here we put a GPA. And here's the thing that's kind of interesting, this thing over here, and you can see it's been declared as a type A node. And what this is this will contain the address of another one of these things. So that, for example, if I were writing a program and I were to say something like A node, my A node equals new A node, and I come over here and I put in 23 and 3.2. Okay, what's going to happen again? Remember, we've got this picture over here of what our working memory looks like. And remember, over here is the stack, and over here is the heap. And what's going on over here is first of all, I've declared a variable in the stack that is called my A node. Now, when I come over here and I invoke this new, what I've done is it's going over here into the heap, and it's finding some free space, and it's going, here's some right here. And what I can do is I can sort of break this up into three pieces like that, and I've got a constructor, and over here is going to be age, and that'll have a 23 in it, and over here is my GPA, and that'll have a 3.2 in it. And again, you can see by my comment over here, we're assuming that the constructor set next to null. So here's the next field, and I'm going to indicate null by just putting one of those in there like that. Now this may be, and again I'm just making this number up, this may be at location 5000 in memory. So it's the number 5000 that gets returned by this call to new, and that's what we put over here in this variable there. Now if I come over here and I say A node another equals new A node 15 2.9. Again, what's going to happen is over here on the stack, I have declared another variable now that looks like this, and this is called another. And what's going on is we come down here in memory, and again, maybe over here at location 4000, it found space for it. And what happens is I put a 15 here, and I put a 2.9 there, and again I have a null value here, and there's a 4000 here like that. And very frequently when we draw pictures like this, instead of putting the address in here like I've done, what we do is we actually draw an arrow to where the thing lives in memory. Okay, so here's what this thing looks like right now. But now I want to do something a little bit different, and I want to say my A node dot set next and I'm going to come over here and say another. Okay, now what that is doing is, here's my A node down here at 5,000, and you can see I've written this method over here called setNext, and what it's going to do is it's going to change this null here, and it's going to put in the value of what another is. Well, another has 4,000, so it looks like that. So in a way, what the picture really looks like now, and let me clean up the screen just a little bit, get things out of the way, is first of all, note that I've got this variable here that's called my A node. And what happens is that actually contains a reference to something that looks like this. (23) 3.2. And then this actually now contains a reference to something that looks like this. 15, 2.9. And a lot of times a null value is represented by the ground symbol, this downward facing arrow like that. So this thing over here, what we have here, this is an example of what's called a linked list. And I want you to consider the following code. I want to come over here and I want to say A node X is equal to my A node. Then I want to write a loop, and I want to say the following. While X doesn't equal null, system.out.println X, and then X is equal to X dot get next. Okay, now again, remember over here we have this method called getNext that for a given node will just return the value of the next reference. So initially what's going on is I've got this variable called X, and X is initially also referencing this node right over here. And notice that I've written a toString method so that when it's pointing here, it's not null. It's going to print out a 23 and a 3.2. But then as the algorithm progresses, we update X, and X is now referencing that one. And again, what we would do, it's not equal to null, so I'm going to print it out. I'm going to see a 15 and a 2.9, and then I say let X get X.getNext, and when I do that, this thing now becomes the value null. Okay, so this is a nice simple loop here for just printing out a linked list. All right, so let's continue along with our discussion of linked lists. And what I'd like to do is actually develop a generic linked list, okay? And it's going to be based on this idea of these A nodes here. So this is taken right from your book, and when your author does the linked lists in the book, he implements it in kind of an interesting and a fairly simple way. So first of all, when we have a linked list, you've got to have something. You have to have a constructor, and the constructor is basically going to take a, we're going to have something that always points at the linked list. We'll call this front. And the constructor just initializes front to that. And that's pretty simple. We're going to need a method to insert. And your author takes a kind of a simple approach here, and he calls it insert front. So the idea being that whenever we insert a new element into the list, in other words, if I've got a list that looks like this, and maybe this is a 2 and a 3.1, and maybe this is a 3 and a 3.3. And I've got some new element here that I want to insert. So I could say that this is referenced by something called new node. And new node might look like this. It might have 17 in here, 2.0. And remember, if it's a brand new node, it's going to look like that. The way that we would insert this is we want to insert this node into the front here. And the way that we go about and do that is pretty simple. First of all, what we would do is we would change this reference here. So that this reference now comes around and points there. And then we would change this reference here so that this thing now comes around and goes there. So we would do this first, and we would do this second. So basically what we would do is we would say new node dot set next front, and then we would say front is equal to new node. So that's pretty easy. And that's insert front. Okay. We want to write another, so this is 1, the constructor. This is 2, insert front. Let's consider other things that we might want to do. We might want to find okay, so let's suppose our linked list look like this. Why don't we make this a little more interesting and put in, say, something like this. 1203, 2.9. Um, 506, 3.1. 3, 1, 2, 7, 2.9, and let's make that the end of the list. So instead of this being just a plain old, instead of this being age as I indicated over here, why don't we change it a little bit, and we could make it an ID, and that's a little bit more interesting. And the reason why it's interesting, I want to assume that these fields over here, the first fields, are unique. Okay, so here is front. And basically the idea is that I would like to find a specific ID number in here. So maybe I want to find 506. Well, the idea is very simple. I'm going to create a temporary variable here. I'm going to call it rover, if you will. I'll set it to the same value as front. And this should remind you, this should be very reminiscent of a linear search. And what I'm doing is I'm basically going, is this it? And if the answer is no, I go to the next one. And I go, is this it? And if the answer is yes, I want to return the reference to it. If the answer is no, I keep on going. Okay? And at some point, I'm going to get a null. So I'm going to come over here and I'm going to say something like the following. I'm going to say let rover equal front. And then I'm going to say while rover doesn't equal null. And I'm going to really write this very much like the way that we wrote linear search. And we're going to assume we're trying to find key, that the name of the parameter coming in is key. And I'm going to say if rover dot get ID, so we're assuming again that this is not age anymore, that this thing is now ID. And we're also assuming that there's a method here to get the ID. So I'm going to go if rover dot get ID equal key. I'm going to say break. Otherwise, I'm going to say let rover equal rover.get next. And I'm going to break. I'm just going to close that loop. Now the question is if I get down here, what can happen? Well, there are two ways to get down here. One way to get down here is I hit break. Okay, that means I found what I was looking for. And if that's the case, I just want to return the value of rover. On the other hand, if I get down to here, that means that I didn't find the thing and rover is null, and I'll return the value null to indicate that I didn't find it. So at this point, I would just say something like return rover. Okay, and again, we're going to write this up formally in a second, but this is basically the way that find works. So we have the constructor, we have insert front, we have find. Okay. We certainly have to have something to print the thing out. Well, we've seen that already. We would come over here and we would say, we would declare a node rover equals front, and then we would just say while rover doesn't equal null, rover equals rover.get next. That one's simple. Okay, that's number 4. I left the hardest one for last. Number 5, which would be delete. So here's the thing about delete. Again, I want you to imagine that I've got a linked list, and again with a unique ID, 1, 2, 3, 3.1, and here's the next one. And here's another unique ID, 352, 1.7, and it's pointing to the next one. 496, 2.1, and maybe that's it. And maybe what I want to do is I would like to delete 352. So you might be thinking the following. I'm going to declare a variable over here. I'm going to call it rover. I'm going to initialize it to what front is pointing at. So this guy is going to come over here and he's going to look at that. And I'm going to go, okay, I'm looking for 352, and is rover pointing at 352? And the answer is no. So what I'm going to do is I'm going to let rover equal rover.getNext. So now rover is pointing over here. And I go, does this equal 352? And the answer is yes. So I go, okay, cool. I found the node that I want to delete. Go ahead and delete it. Well, the question is how do I delete this node? Well, the answer is if I want to delete this node, I've got to take this reference here and I've got to change it to do that. Everybody get it? And if I want to change this reference over here, I need a reference to this node as well. So the point is just having one reference traversing the list is not enough. What I actually need are two of them. And let me get another screen here to kind of make this point. What I need is something that's going to happen like this. I want you to imagine, here's this. So here's a linked list. And what I want to do is I want to basically maintain two pointers. I want to have a pointer called rover. And I want to have a pointer called previous. And basically it's going to be like this. If previous is here, then rover should be here. And I think you can see if I'm at the situation that I want to delete this node here, then this thing is right before it. Now, if on the other hand, this is not the node that I want to delete, I've got to move everything forward. And how am I going to do that? Well, what I could do is I could set previous to rover, and rover could be rover.getNext. So basically, I might want to do something like the following. And again, I'm just sort of thinking out loud now. I might say something like, while rover doesn't equal null, and I come over here and I say something like if rover.getID equal key break. Otherwise, what I want is I want to set previous equal to rover and rover equal to rover.getNext. Everybody get that? So then what happens is if I get down to here, I've gotten down here in one of two ways. I've gotten down here either by executing the break, which meant that I have found the key that I'm looking for and I actually want to do the delete, or rover makes it to null, which means that if rover makes it to null, I haven't found what I want to delete. So first of all, let's agree upon something. If I'm going to delete a node, I want to return a reference to that node. Okay, that should be the return value. And if I can't find the node that I'm looking for, I want to return null. So the thing that I do over here at the end is I might say something like the following. I might say if rover doesn't equal null, okay, I might say something like the following. I might say prev.setNext to rover.getNext. How cool is that? Think about that. What I'm doing here is I'm saying prev.setNext. I want to change this reference right over here, and I want to change it to rover.getNext. And that has the effect of doing that. Okay. In either situation, what I would want to do is I would want to return rover. Well, this is all kind of clever, and I think I'm close to being done, but I have a couple of questions. So the first question is how do I initialize previous and rover? And then the other question is, suppose the list is empty. Well, here's my guess. My guess is I want to set previous equal to null, and I want to set rover equal to front. And if I do that, this all kind of seems to make sense. Let's just think about a couple of cases here. So let's consider a couple of bad cases. Suppose I have something that looks like this. There's something in here. And suppose it's just empty like that. And suppose I want to delete. So I'm just talking about a list with one element in it. So suppose I want to delete 200. So the point is there is nothing. It's not going to find this. So I come in here and I let previous equal null. I let rover equal front. I go, well, rover doesn't equal null. I say if rover.getID is equal to key break, well, it's not true. Previous is going to equal rover. Rover is going to be rover.getNext. So if I come over here, if rover doesn't equal null, well, it does equal null, and I just return null. So this case works out fine. Or I should say this case works out fine. Suppose I want to delete 123. Now I've got a problem. So with trying to delete 123, I've got a problem. What is going to happen over here, let's go back to our algorithm. I am going to execute the break the very first time. Remember, previous will be null, rover will be pointing right at this thing. I come over here and I execute the break. Well, if rover doesn't equal null, and what's going to happen over here is I'm going to be attempting to set next on prev, but prev currently is null. So I need to rethink this logic over here. And the way that I'm going to rethink the logic is it's going to look something like the following. I'm going to consider a couple of cases, and I am going to say the following. I'm going to say if rover doesn't equal null, okay, then what I want to do is I want to break this up into some cases. So I come over here and I say if previous does equal null. So remember what this means. If I make it from here, if I make it to this situation here, that means that the linked list only has one node in it and I'm trying to delete it. And of course what I would want to do here is say front is equal to null. Else, okay, this, if I get over here, previous doesn't equal null, and this statement over here makes perfectly good sense. So I could say previous.setNext. And I apologize for running out of room here. I could say previous.setNext to rover.getNext. Okay. And in any case over here, I would return rover. Okay. Now that's almost the whole thing. The only other thing that I would need to worry about over here is I think before I even enter this loop, I want to check right here and say, is the list empty? Suppose I initialize previous to null and rover is set to front. If it's an empty list, that's already null. I come over here and it says, well, while rover doesn't equal null, well, it is null. So I would come all the way down to the end of the loop here, and it would say, if rover doesn't equal null, go do all of this. Okay, it's not going to do any of that. It's just going to come over here. It's going to return null. So this works on the empty list as well. I'm pretty confident of this, and I'm going to stop recording now, and the next thing we'll do is we'll just type this all in. We'll get the real code going. Okay, did a little typing. Here's the complete linked list class right here. Let's just talk this through a little bit. Again, I'm assuming that this int age has been replaced by ID. We'll make that unique. We'll assume that there's a method in here called getID. But so here's the constructor right over here. First of all, we have a private anode front. That's the thing that points at the linked list. And our constructor over here just sets that equal to null, as indicated by that picture there. Here's the code to do it here. We had this thing called insert front. Okay, and the way that we insert the front, this is the new node that we want to insert. Okay, we have that point to whatever front was pointing at. Remember, initially front would be pointing here. Here's my new node, and I want to set that equal to what this was pointing at. And then I want to change this pointer over to here. So that's exactly what's going on over here. Note that this code over here is fine even if I'm inserting a new node into an empty list. Okay, so that is that one. Here is print. Okay, and we can see that this is just a simple loop starting at the beginning of the list, and we keep printing out nodes until we hit the null pointer. Over here is find, and you can see again this was written very much like our linear search of an array, except in the array when we went backwards, here we go forward. If we find what we're looking for, we break out of the loop, okay, over here, and we would return rover. On the other hand, if we never execute this break statement, rover would finally get the value null, and we would return a null. That would get returned here. So basically find either returns a reference to the node that we were looking for, or it returns a null reference. And then finally, here is delete right over here. As we indicated before, when you want to do delete, you actually need two sets of references. Rover is looking for the node we want to delete. Previous is always one node in back of it. Because if we find the node that we want to delete, we need to go to the one in back of it and update that pointer. We do that right over here in this line right over here. Okay? So basically, we're doing just like before, we're doing our linear search, which is very similar to what we did over here, except that we're updating these two references. When I get down to here, I can get down to here in one of two ways. I can get down to here and rover is null. If rover is null, that means I didn't find the node that I wanted to find, and I just return null. If on the other hand I get down to here and rover doesn't equal null, I have two situations that I have to worry about. If rover doesn't equal null, that means that there are elements in the list. And there are two possibilities. There's either one element in the list or there's more than one element in the list. If there's only one element in the list, then previous would be null and I need to change front. If there's more than one element in the list, okay, or I'm deleting the first element in the list, okay, I'm still going to do that one. If I'm not deleting the first element in the list, I'm going to come over here and do that one. I would welcome you all to type this in. If you can't read this here, it's in your book. Create a linked list and have some fun with it.